Today we're going to look at projectiles that are launched at an angle from the ground. I'll often just call them angle launches. The difference between this type of a problem and a horizontally launched projectile is that in this problem, the object, the projectile, will start at the ground level, on the ground. We will be launched at an angle relative to the ground, and will travel along a classic parabolic path, the kind of motion people are used to seeing as objects are flying through the air, baseball, football. Notice what happens though. This object is going to be launched, and if we assume it's a red cannonball flying through the air here, and we look at different moments in time, it's going to follow this path as it goes from its initial point to its impact point. It lands back at the same elevation from which it was launched. So with the horizontal problem, I use the phrase height dictates time. Well, we're on the ground, so height is not going to dictate time. What's going to happen in this case, though, is we no longer have just a horizontal initial velocity. We're launching at an angle. So that means that when this cannonball launches, it has both x and y velocity, initial. Neither are at zero. And what's going to happen is the velocities in each direction are going to dictate what happens from that point on. So the first step is understanding what we have to do with this initial velocity in terms of separating it out to determine, well, how much of this velocity is in the horizontal direction and how much of this velocity is in the vertical direction. And that's how we start the problem. The typical questions that are asked with this type of a problem are, what's the maximum height above the ground that the projectile reaches? How long is it in the air? Where does it land horizontally? So you're seeing the same type of questions. You're going to be approaching them a little differently because we have a different setup with the problem. The easiest way to solve a problem of this type is to actually do a problem of this type. So what I want to do is show you the fact that when you look at these types of problems, the initial information is really sparse, because if they give you the initial velocity and they give you the angle, gravity's in the driver's seat from that point on. That's all they need to give you. If you have both of those two things, the path has been set. It's going to land at a certain spot, it's going to spend a certain amount of time in the air, and it's going to go to a certain maximum height. So what I want to do is talk about, if I give you some initial conditions, we're going to look at solving, hey, what's the max height? What's the time in the air? What's the horizontal distance traveled? So let's start here. Let's say that we give this thing an initial velocity of 500 meters a second. And we're going to go 30-degree launch angle. This is a 2D vector. Now we've already done two-dimensional vectors, so we know the fact that if we have a two-dimensional vector, we can break it into its two components, its x and y components. That's going to allow us to put in the initial values of how fast is it moving in the x direction, how fast is it being launched vertically or in the y direction. So we got to look at this. And this is where you got to remember the SOHCAHTOA stuff. If we are launching at 500 meters a second, and we have a 30-degree angle here, this component is the VIX. It's the initial horizontal velocity. This component is my VIY. It's how fast this thing is being launched from the ground initially. And remember, this is a technique to break up how much of the 500 is pushing the projectile this way and how much is launching it straight up. So we need to use that information to get the VIX and the VIY. That sets the stage for everything else. Now, we've done SOHCAHTOA so many times, I'm not going to rewrite the equations, but notice the VIY is the opposite to the 30-degree angle. So that's going to be the sine function. So if I say the sine of 30 degrees is opposite over hypotenuse. That's going to give me what the initial vertical velocity is. So again, 500 times the sine of 30 is going to be your initial VIY. Sine of 30 is a half, so you're going to be going 250 meters a second vertically. So I'm going to come back over here, and my VIY is 250. So that's good. You can use Pythagorean if you want. I'm going to look at the fact that the VIX is the adjacent side to the 30-degree angles. So I'm going to say the cosine of 30 is VIX, the initial horizontal velocity, divided by the 500. And again, you're seeing the whole cross multiplication theme happening here. So 500 times the cosine of 30 is going to give us that initial horizontal velocity. So let me punch some numbers in here. 500 times the cosine of 30. Okay, that makes more sense. 433.01. It had to be larger than the 250, so that makes more sense. 433. So now we have the starting velocities. So now I'm going to go bye-bye to this stuff. So what is happening here is when this launches, this is how you can think about it. It has a horizontal velocity of 433.01 meters a second. At the same time, it's moving upwards at 250 meters a second. So it's doing this at the same time. It's going up, coming down. So it's being launched to the right and also moving upwards. The 433 just lets you know how far downrange this thing's going to land. The 250 is the vertical velocity. That's going to dictate the time in the air. With this problem, if you look at the fact that this thing goes up and comes down, and notice the point at which it looks like this is a mirror image is right down the middle of this arc. Well, this is max height, isn't it? MH. So what I want you to think about is what defines when something reaches maximum height. Again, it's a vertical phenomenon. So if you're at max height, have you just lost all your velocity? Have you just removed the last little bit so it can't move up any higher? The answer is yes, you have. So when you get to look at the special condition of maximum height, you want to remember that when a projectile reaches what is called maximum height, the final velocity in the y direction is 0. So just for a moment, that's what I'm going to call my final velocity. Now we bring in the equation that we didn't use before, is I'm going to figure out what's called my halfway time. So what I'm going to do is, if you look over at this table now, we got to be careful because I'm maybe using two different things here. If I want to solve for maximum height, the reason I'm doing this first, kind of hang with me for a moment here. I'm going to use this to figure out the time it takes to get to this point. And because the projectile has to come back down, it's the same amount of time to come back down. So if you know the time to reach max height, you can just double it and you have the total time in the air. If it's 2 seconds to get up to max height, it's going to be 2 seconds to come down. So this is a very critical point to be mindful of. So what we're going to do is we're going to look at solving for the time it takes to get to reach max height. So time to max height. And I'm going to use this. VFY equals VIY plus AT. Now this is going to be a T1 half. I want to make sure I note that, hey, that's the halfway time when I'm looking at this. Well, I haven't done a lot over here, so let me start filling things in again. Acceleration in the x direction, 0. Acceleration in the y direction, we use -10. The velocity in the x direction, well, unless something changes, we're moving at 433.01 until it hits the ground. Now, if we're solving here, here at that point. The y velocity at that one location is 0. So if I put a 0 in here, I have to be mindful of the fact that this is allowing me to solve for my t1 half, and only my t1 half. So if I start to solve this now, it's going to look like this once I stop erasing stuff. We're going to have 0 velocity at maximum height. We're leaving the ground at 250 meters a second. The acceleration in the y direction is going to be -10. And this is going to tell us the halfway time, the time to reach maximum height. Numbers are looking really nice here. So -250, because you're going to subtract 250 from both sides. Divide that by -10. This is going to give you your halfway time. So 25 seconds is the time it takes to reach max height. So 25. So it's going to 25 in that too. This is the key. Once we have this, max height, super easy. Horizontal distance, super easier. So follow this one. Maximum height, well, if we want to look at the maximum height, we're doing this, right? The change in y is our VIY times the time. Now remember, this is the halfway time, because we're max height. A lot of subscripts. Just hang on. 1/2 AT squared, right? And that's a 1/2 also. So let's supersize this so you can actually see it now. My initial vertical velocity is 250. My time to reach maximum height is 25 seconds. If we're using -10 here, this is a -5 because 1/2 times -10. And now we're 25 seconds squared. So now let's start plugging in, let's start punching some numbers. So 250 times 25 gives me 6,250 meters it would travel without gravity. Then we bring the gravity term in. So now we have 25 squared times 5 minus 3125. So this thing is cooking. It's gonna reach a little bit over 3 kilometers above the ground by the time it reaches maximum height. So we sent this thing hauling in the vertical direction. Notice I only used the information in the y column because I'm looking for this. Now this is my maximum height, is 3125. That's my change in y. There's a shorter way to do this, guys and gals and people. If you remember that we go back to, you can also say the displacement is the average velocity times time, right? So it's kind of unwritten equation 3 here that we're using. Well, you know what the average velocity is going to be in the vertical direction. It's 125 meters a second, right? So blam, 125. What's your time? 25. Could it work? I don't know. Sometimes I think it depends on the day. Okay, let's see. 3125. So you can solve either way. If you want to use the average velocity, you got to remember to take these two, divide by, add them up, divide by 2. That's max height. The last one, you do exactly the same fashion that you did for the horizontal. So I'll finish up with that so you kind of see what's going on here. So now I'm going to use this equation again, and what we're going to say is the horizontal displacement. Now remember, with this equation, this long equation, there is no acceleration in the x direction. So your VIX times your time. Now be careful, I'm going to even circle this. This is the total time, not your halfway. So you have to take into account the fact that the time we used here was the height it takes to reach, quote, the halfway point, because that's when maximum height occurs. I want to know how far this thing travels. So I'm not using the t1 half. I'm going to be coming over here and saying, okay, this is my average velocity in the x direction, never changes. 433.01. 25 seconds up, 25 seconds down, times 50 seconds. So 433.01 times 50, 21,650.5 meters. So it's this thing's moving. So this is a pretty serious cannon here. In review, all these problems are done the same way. And what I would suggest you do is, number one, break down this vector into components. Get your x's and your y's. Vertical velocity will tell you how long you're in the air. The vertical velocity will help you figure out the time to maximum height. Once you have the time, it's downhill from there, because you use that time in here to get the height. Again, looking at the y column only. When you want to know how far it's going to travel, take your halfway time, double it, plug it in the v of t equation, or just remember, you're looking at the first term of this equation here. If you can handle a problem like this, as far as the structure and the layout, you're in good shape. Bye-bye.